Hi everybody, welcome back. This is Dr. Lefkoff here with another installment of Intermediate Microeconomic Theory. And this is the second part of a two-part segment where we've been analyzing the repeated prisoner's dilemma. The first segment, last video, we had analyzed the repeated prisoner's dilemma in the case where it was repeated a finite number of rounds. And what we're going to do in this video segment is we're going to extend the analysis to an infinite number of repetitions. But before we do that, let's just recall where we had come from. So the problem we saw last time was that in the case where the game was repeated a finite number of rounds, there was a fundamental breakdown of the potential to cooperate in the sense that the subgame perfect equilibrium of the game was that the players would deviate in every period, and we saw this was not optimal. And the driving force behind the deviation was the fact that there was really at some point no more future where players would have to worry about any potential retaliation from deviation. So this was the problem. Players in the last period would always have this incentive to try to just deviate and steal the payoff pie for themselves and not worry about any repercussions. So given that that was the problem with the finite framework, let's see if extending the analysis of the game to the case where it's repeated infinitely would perhaps mitigate this problem where we see the potential to cooperate breaks down immediately. And so all we're going to do is we're going to try to model the strategic interaction in a way where there was always a future. In that case, if any players deviate at any point, they'll have to potentially worry about the threat of punishment in the future from other players. And recall that this element of having a future, this was not present in the finite game when we reasoned out the outcome using backwards induction, because at some point the game would end. So we're going to consider this case now as we extend the model to what we call an infinite horizon framework, where the game is repeated not once, not twice, but we're going to repeat it an infinite number of times. Okay, so we're moving to the infinite horizon framework. And the infinite horizon framework is useful for modeling two types of situations. The first you can think is literally a game that never ends. And you might think, well, in what situations realistically, do players live forever? And the answer is that players might not. But for example, when firms are competing with one another, the manager of the firms might die off, but the firms arguably, could live on forever and should be run accordingly. You wouldn't want to run a firm as if it's going to die tomorrow. Then you might, be inclined to run it in a way that drives it into the ground. So, for example, we're going to see an oligopoly competition later on that the infinite horizon framework is actually a very convenient framework for studying the interaction of oligopolies and cartels. The other type of framework where infinite horizon games are useful in describing strategic situations is a framework where you have a finitely repeated game. However, the termination or the end of the game is actually uncertain and not known to players. So just remember that in the finite game, all players had common knowledge of when the game would end. It turns out if we get rid of that common knowledge, so that the players maybe face some uncertainty, some probability that the game could end in any particular round, then we actually induce behavior consistent with actually having the game played infinitely, literally infinitely, in that players always have to worry about when the game will end. Is it going to end? Is it not going to end? If there's some probability it's going to continue, then there's potentially a future that I have to worry about. So the way I'm going to play now should be conscientious of having a future. Okay, so all we're going to do now is we're going to take a look at the games from sort of a different perspective than we've been looking in the meantime. We're going to look in what I'm going to refer to as payoff space here. So in this diagram, we have the payoff to the column player on the vertical axis, the utility or payoff to the row player on the horizontal axis. And all we're going to do is we're going to look at every possible outcome, and we're just going to plot the payoffs to each player according to each outcome. So the first outcome here we're going to look at is if both players choose D, deviate, then both the row player and the column player each get a payoff of 1, so that must be this point on this diagram here. And we can also consider the point in this payoff space that corresponds to the situation where both players choose to cooperate, and that's this point 5, 5. And then we can also likewise consider these off-diagonal boxes where one player deviates and the other player receives 0. Okay, so this case is the case where column player has deviated against row player, so column gets 7, row gets 0. And last but not least, we have the case where row player deviates against column, and row gets 7, column gets nothing. Okay? So if the game is just played once, then these are the sort of the 4 possible payoff outcomes that we can observe after just one static round of this game. Okay, so what we're going to do next is consider what happens if we play this game over and over again, and we're going to sort of show that the set of possible points that we can generate actually becomes much richer than just these 4 points that we can generate if we only were to play the game one time. Okay. So what we're going to do next is we're going to take a look at average payoff space. And as I just mentioned, if the game is played one time statically, then we can only wind up realizing a payoff vector at only one of those 4 points in terms of the sort of the scores of the utilities to either player after just one round of play. So I want you to now think that if we were to repeat the game T rounds, okay, or some number of rounds, and we added up the player's utility, or we added up their payoffs over all these rounds, and then divided them by the total number of rounds to compute the average payoff. Okay, I want you to imagine now that's what we're going to plot in this payoff space. We're now going to look at the average payoff by considering the average payoff to a player for a particular repeated strategy combination or repeated strategy profile. Okay, so this is what we're going to do. We're going to consider repetitions of the game, and then we're going to see as we repeat the game that essentially means we're going to be moving around these 4 different points in average payoff space, and as we move around the 4 different points, we're going to show that we're actually able to generate other points in that space as well in terms of the average payoff to a player in the repeated game. Okay, so the idea is that repeating this game is going to allow us to support average payoffs that are in that space. Okay, and it turns out that these average payoffs are going to fall within the interior of these 4 points, which again were the only 4 points we could wind up at if we only played the game once. And we're going to call this interior space of these 4 points that we're going to generate by considering average payoffs. We're going to refer to that as the convex hull. So the next couple slides are going to be focused on generating a feasible average payoff set, this convex hull set in payoff space. Okay, so we're back here. Here are 4 points. Just remember, it's very easy to consider which strategy outcomes these correspond to in the static game. Okay, but now what we're going to do is we're going to consider how we could generate average payoffs that are outside of just the set of these 4 points. And the way we're going to do that is by allowing these players to maybe cooperate on a particular scheme, where the players maybe alternate between certain boxes in the static game. So they're maybe over here alternating between these 2 boxes, or maybe they're switching here and here, or here and here. Okay, but we're not going to worry so much why they're doing this yet. We're just going to show that if they alternate in a particular fashion, that we can generate some average payoff vector that's not at exactly one of these 4 points, but that's maybe somewhere in between. So let's first consider this the following strategy combination, this following strategy profile. Let's suppose the row player and the column player decide to take turns letting each other deviate against one another, meaning sometimes column player is going to allow or is going to be able to steal the payoff from row player. Row player will allow this, and then the other half of the time, let's suppose row player gets his turn to steal the payoff from the column player. So here's what's happening. The row and the column player are alternating between these points at approximately 50% intervals. Okay, so half the time they're getting 7, half the time they're getting 0, which means on average they must be getting about, good, you guessed it, 3.5 utility, right? So you'll notice by alternating between these 2 points here, okay, which corresponded to alternating between these 2 boxes in the static game, okay, we were able to generate a payoff vector that was not one of these original 4 points, which was one of the original 4 payoff vectors of the static game. So the point is we were able to generate some payoff vector as an average of the other payoff vectors of the static game. Okay, and this one happens to be for the case where we exactly spent about half the time between these 2 boxes over here. We spent a uniformly 50-50 alternating. So maybe you could think these players took turns alternating every other turn. They switch back and forth, or maybe every 2 turns. There were 2 turns here, then 2 turns here. Okay, but the point was, at that frequency, when they were about even distribution of how much time they spent in either box, that gives each player an average payoff of about 3.5. Now you can imagine if the player spent more time relatively down in this bottom left box where row player is making 7 and column is getting 0, okay, then obviously this point would be pulled a little bit down further towards this point 7, 0, where row player is making 7 and column player is not getting anything. So again, when they were alternating 50-50 frequencies across these 2 boxes, they wound up getting this payoff sort of right in the middle of this line. But now we can easily see that they could have generated any payoff on average along this line by controlling, in a sense, the frequencies with which they're cooperating in these two boxes. Okay, so that's one particular scheme where we've generated an average payoff vector of 3.5 for each player. Hey, but that's not all. You could easily consider doing the same thing between these 2 points. Right, suppose, and again, don't ask why, but just suppose the players decided, or they arranged on alternating between these static strategies over and over and over again, which means on average, again, they're going to be able to generate this payoff vector where the column player is getting on average 2.5 and the row player is getting on average a payoff of 6. Okay, and again, we argued, for the last example, that we could generate any payoff on this line just by changing the frequency with which the players agree to remain in one box versus the other. Okay, so hopefully you're getting the point. We can keep doing this. Maybe they had done some alternating regime where they were considering, coordinating by moving around these strategies in the static game, which means on average they would be able to generate this particular payoff. And again, by changing the frequency, they're in those light blue boxes in the right-hand side game over here. They can move around this line, on average. And hopefully you're starting to see the picture here. These 2 points, by alternating from those strategies, we can generate this average payoff vector. By moving between these 2 points, we'd be able to generate this set of average payoff vectors here on that blue line. Okay, so you get the point. Right? By alternating, or by moving ourselves around in the static game, we're generating some average payoff vector here in the repeated game. Okay, so let's just suppose we plotted all those points. Okay, so these are us alternating again between initially these 4 points here that we're defining the payoffs in just one repetition of the static game, and now we can generate these other points in between. Okay, but we could even take it one step further and argue, well, man, if one particular repetition scheme puts me here, and one particular strategy profile puts me here, then I could also alternate between those alternations, right? Let's do this for 10 rounds, let's do this for 10 rounds, let's do that for 10 rounds, let's do that for 10 rounds. And then you'll notice we start generating a lot more average profiles. Here, average payoff profiles here that correspond to a particular strategy combination. So here's the idea. Given a particular static game, we can identify sort of those finite set of points where we can wind up in terms of the payoffs to players from playing one round. But when we extend the static game to an infinitely repeated framework, then we can think of the payoff space as measuring the average payoff. And the average payoffs that are feasible in the repeated game then turn out to be this entire set here, right? And we argue that because we can take any type of weighted average of any particular payoff in the static game to generate some point in between there. Okay? So we refer to this set here as the convex whole of the payoff set. And you'll notice that term convex, that sounds a little technical, and I mentioned I'm going to try to provide more of an intuitive explanation here, not so much of a technical one, but the nature of infinitely repeated games means the explanation is going to be just a little bit more technical than compared to when we explain the outcome of the finitely repeated prisoner's dilemma. So they say this set is called the convex whole of those original 4 points, and all the convex whole is, it's the set of points that you could generate by connecting any 2 points in that space with a line. Any 2 points in a convex set, you can connect them with a line, and you can check if you pick any 2 points in this blue diamond region, you can certainly connect any of those 2 points with a straight line. All right, so we're getting somewhere. We've seen here now that the set of feasible average payoffs in the repeated game does fall within this convex whole of the static game's payoff vector. And moreover, given some payoff vector in that blue region, we can always construct some strategy that can support that payoff vector. Now, this last statement here in the second bullet point sounds a little backwards compared to what we had done. We had looked at a particular strategy and showed that that particular strategy corresponded to a point in payoff space. However, what this bullet point suggests is we could have just done the opposite. Let's pick a point in payoff space. We must be able to construct some strategy, right? Some strategy profile by alternating around in those boxes of the static game that would generate that average payoff vector, and we can certainly do that. It's definitely a two-way street in that regard. Okay, so you give me a strategy, I can give you a point in this space. You give me a strategy, I can give you a point in the space that it corresponds to. Or likewise, you pick a point in the space, and we can then construct some regime over in the static game some sequence of how we would alternate in the static game that would be able to generate a given payoff vector over here in the convex hull region. Okay, so this is where we were. And hopefully one thing that you'll notice is that if you looked at that convex hull region and you asked, well, there are some areas of that convex hull region that seem to benefit one player more than another and vice versa. Okay, one question would be, which payoff vectors would be acceptable to players if they were going to try to cooperate with one another? Okay, so this is sort of a subtle question to ask here. And we're going to actually introduce a new concept at this point in order to answer this question. So I'm going to informally define this concept. This is actually, there's a more technical, formal definition of this concept, so this is a little bit of hand-waving on my part here. But I'm going to informally define what's known as the min-max payoff vector as the lower bound on the maximum payoff you could guarantee yourself in the event your opponent was trying to punish you as harshly as possible without any regard for themselves. Okay, so again, it's the lower bound on the maximum payoff you could guarantee yourself in the event your opponent was trying to punish you as harshly as possible without any self-regard. All right, so you can imagine this should be the least payoff that you should ever have to tolerate in terms of the average payoff you would get if you agreed to cooperate with anyone in the infinitely repeated game. Right, so if somebody says, hey, let's cooperate, you'll get this payoff and that payoff. Okay, that's all well and good. However, if I'd be better at not cooperating with you and just taking my min-max payoff, I would rather do that. All right, so what we're going to do next is we're going to identify this min-max payoff. Okay, and again, the way we're going to identify it is by asking ourselves, what is the minimum payoff we would really have to tolerate in this game? Okay, so let's pretend like we're the row player for a second and ask ourselves, if the column player tried to punish us without any regard for himself. So if the column player wanted to punish the row player, okay, what would the column player do? Well, you'll notice if the column player plays C, okay, he's letting the row player get a 7 or a 5, which is not too bad for the row player. Okay, but if the column player was to choose D, then notice the best the row player can get is a 1, and the worst you can get is a 0. So if the column player wanted to punish the row player, the column player would choose D. Okay, so that's the column player trying to minimize the row player's payoffs. Now, given the column player is trying to hurt us as the row player, what can we do to defend ourselves from this? And the answer is, oh, well, column player should just play D then, right? He should play D. Or, I'm sorry, row player. If we're row player, we should play D. Because if column player is playing D to punish us, okay, us playing D against that is really the best defense because we guarantee ourselves a minimum payoff of 1 as opposed to getting this payoff of 0. All right, so hopefully you thought about this and said, well, man, the lowest payoff I would ever have to tolerate in the repeated game on average is 1. Right? So that's the minimax payoff vector. Okay, which means if I'm going to cooperate at all, right, if there's going to be any hope of cooperation, whatever strategy we choose has to yield me a payoff. In fact, it has to yield at least all players this payoff. Okay, so this purple region here, this region identifies the set of payoff vectors that are at least as good as that min-max payoff for both players. Okay, now all we're going to do is we're going to look at the intersection of this set with the average feasible payoff set, which was that diamond region we had drawn before. So now I'm going to just go ahead and look at that. Okay, and we're going to refer to this as the set of average payoff vectors that are both feasible and individually rational. Okay, so let me just back up for a second here. This purple region we're going to refer to as the set of individually rational payoffs, in that they're individually rational in the sense that players would be willing to accept them since they're at least as good as the min-max payoff, which is the minimum you could guarantee yourself by not cooperating. Okay, so again, this odd-shaped region here now that we're looking at, the subset of the big purple region we looked at on the last slide. Okay, this region here is the set of feasible and individually rational payoff vectors. Okay, and again, as I mentioned, you can pick a point in this region, and then we can always construct some strategy that would support that point as the average payoff to the players. Okay, now one thing to note here is that this orange region, okay, corresponds to payoff vectors that one player or the other would reject since they would be worse off in that orange region than accepting the min-max payoff. For example, the row player would never accept a payoff over here because it would be giving him an average payoff less than 1. Okay, and he would always do better just by playing D and getting his min-max payoff here of at least 1. Okay, likewise, column player would never accept a strategy combination that would put him in this orange region. For the same reason, this orange region would give the column player a payoff again on average of less than 1, and he would be better off just by playing D and collecting his min-max payoff here. Okay, so what we're going to see next is that it is possible then for us to cooperate in this purple region where we've constructed now the set of payoffs that are both feasible and individually rational. Okay, these are generating at least the min-max payoff and they're feasible. All right, so now what we're going to do is we're going to take a look at a theorem that allows us, in a sense, to solve the repeated game. And this theorem is known as the Folk Theorem, and I'm going to again go through a very informal explanation here. Okay, but the Folk Theorem is a very powerful idea that, when formalized, suggests that any strategy combination can be supported as a subgame perfect Nash equilibrium in any repeated game, in any infinitely repeated game. Okay, so it's a very powerful idea. Any strategy combination can be supported as a subgame perfect Nash equilibrium in any infinitely repeated game. And again, there's always a caveat, and the caveat is 2 conditions, and the conditions are as follows. The first condition is that the resulting supported average payoff vector is individually rational for all players. Okay, so we got to be in that purple region. And again, we just saw that this meant that each player gets their min-max payoff, which was that lower bound that you could always guarantee yourself if the other guy was trying to punish you as harshly as possible. Okay, and this payoff was 1 in regards to this particular parameterization of the model that we're using. Right, so this is the condition that really we've sort of been working on here by looking at this diagram. Okay, so now we know, hey, if we're in that nice purple weird quadrilateral region, right, the Folk Theorem is going to tell us that we can actually support that strategy that put us in that region as a subgame perfect equilibrium strategy in the repeated game. Okay, now the second condition, which we're going to discuss more about in a second, is that all players are sufficiently patient. Okay, and I'll elaborate more on what that means. It sounds like it has to do with psychology, and it does a little bit. Okay, so we'll talk about that in a second. Okay, but for now, I want you to think about the obvious solution to this game, or at least one obvious solution. We know that the Folk Theorem here has told us that there's actually infinitely many solutions. Okay, but hopefully you remember an obvious solution would be to say, hey, why don't we just play the efficient outcome in the static game? Let's do that every time. Let's each just play C every round forever. Okay, that's one particular strategy combination. And again, this was supporting the efficient outcome in the static game. And I'm going to show you that this strategy combination puts us in that purple region, which means it's possible to actually support it as an equilibrium. Okay, so the idea now is that in the infinitely repeated game, it might actually be possible for us to cooperate in an equilibrium, whereas when we repeated the game finitely, it was impossible. All right, so let's go back to this average payoff space. Here's our set of feasible and individually rational payoffs, and you'll notice that the strategy that we had talked about, let's place that top left box CC every period, that's right there. Okay, it's in the top right of that set, so certainly the Folk Theorem is telling us that it's possible then to support this strategy of cooperating every period in the infinitely repeated game. So let's talk a little bit more about the consequences of the Folk Theorem. Okay, one consequence we just saw is that there are infinitely many candidates in terms of subgame perfect equilibrium strategy combinations. Okay, infinitely many, so a lot of searching to do, which means the fundamental question when you're dealing with an infinite game isn't really, is there an equilibrium? There's infinitely many of them. So the question really is, for a particular strategy combination that we've shown satisfies that criteria of falling in that purple region where all players are getting at least their min-max payoff, is it possible that the players are also patient enough so that they satisfy condition number 2 of the Folk Theorem so that we can support that particular strategy as a subgame perfect Nash equilibrium? Okay, so the nature of the question has changed a little bit here. It's not really, can we have an equilibrium? We know we can. It's how patient do the players need to be in order to support that particular strategy combination as an equilibrium. So here's the next thing we're going to look at. Okay, we're going to try to get these guys to cooperate by playing C in every period. Okay, so one natural question is, well, what other incentives do they face that might destabilize this cooperative regime? And one thing you might be thinking is, well, man, I could still deviate and play D, and I can get an extra payoff of 2 that period. So the incentive to deviate is certainly still there in any given period. Okay, and, now that there's a future, what do I have to lose? Well, if I deviate, okay, now the stakes are a little bit higher because the other player might not like this, and they now have an opportunity to punish me since there's always some future that I have to be concerned with. Okay, so we're going to talk about a punishment phase. Now, we're actually going to assume a type of punishment phase. So I want to be very clear here that this is an assumption of the model that we're using. So this is actually a component of the model, is the punishment phase. All right, and we're going to start by assuming the worst case scenario type of retaliation, since it turns out to be very mathematically convenient. And as we know, anytime we're building a model, it's easier to start from with simple building blocks and make things more complicated later. So the harshest punishment that we can possibly assume here is that once any player deviates from playing cooperate, okay, the other player, after being cheated, is going to retaliate by playing deviate forever. Okay, so we're cooperating. If anybody cheats the other person, if anybody switches to deviate and tries to steal that payoff of 7 by gaining that extra 2, okay, then they're going to get punished forever. Okay, this is what we're going to assume happens in the punishment phase. Okay, and we're going to assume this is going to happen, even though you might say it's not necessarily in the other player's incentive to punish you, because that might hurt them also. Okay, we're not going to worry about that right now. We're going to assume, we're going to take this punishment phase sort of as an exogenous factor, and we're going to say, given the punishment phase, we're going to ask ourselves, how patient do we need the players to be in order to want to still cooperate? Okay, so this worst case scenario punishment phase, it has a sort of a famous name in the literature. It's often referred to as the Grimm trigger strategy, or the Nash reversion strategy, and the idea behind the name is that once it's triggered, once somebody deviates, then you revert to this phase where you punish the person perpetually, and you never go back to the cooperation phase. Okay, so there are, of course, other ways to punish players that maybe aren't as harsh. For example, there's another type of strategy, or a punishment phase rather, known as a tit-for-tat punishment phase, whereby you punish somebody for maybe a couple periods, and then you allow them to come back into the cooperative regime, which is sort of not as harsh of a punishment. It's a lighter punishment than trying to just punish them forever. And these are more complicated mathematically, and you'll handle these in a pure game theory course like Econ 109. So for the meantime, for our purposes here, it turns out that assuming the harshest punishment actually does have an advantage for us, in the sense that it will actually help us establish a lower bound on how patient we need players to be in order to cooperate. Okay, and you might think, well, what's he talking about? Hopefully, the discussion coming in the next few slides might clear this up. But in the meantime, what I mean by establishing a lower bound on how patient we need players is the following. If the punishment was not as severe, right, if you're not going to be punished as severely, then you might be more likely to then deviate, right? If I do something bad and I know I'm not going to be punished, I'm going to be more likely to do something bad. So the idea is that if the punishment isn't as severe, then we would need the players to want to be even more patient, in a sense, to want to compensate them for the temptation of deviating, right? So if the punishment isn't as severe, I might need the player to be even more patient in terms of not being short-sighted and wanting to steal that payoff now, and sort of ignoring this fact that I can punish him later. Okay, so let's talk about the trade-off now that you face from deviating from the cooperative regime. So here's the idea. Okay, we're cooperating. Okay, and these are the rounds here on the x-axis. Okay, so cooperating, and then all of a sudden we get to a particular point in time, and let's suppose this is from our perspective as the row player. Let's suppose we deviate. Okay, so we get to this point in time, and then we deviate. Okay, notice when we deviate, our payoff immediately that we get in that particular period jumps up to 7. Okay, however, the other player's payoff, when we deviate against him, he sees it. His payoff is going to wind up dropping to 0. Okay, and then immediately after that, we're going to move into this punishment phase where the other player is going to try to punish you as harshly as possible, which means he's going to play D. Okay, and we're going to obviously play D to defend ourselves against that. So in the punishment phase, we revert back to this equilibrium payoff from the static game of 1. Right, but here was the idea. Cooperation phase, we were playing CC, then I deviate, I choose D that period, other player sees that, and then we revert back to this punishment phase. Okay, so the trade-off from deviation should be very clear. Right, when I deviate, okay, I get this immediate jump in my payoff that period, so that's my immediate gain. Okay, however, in all the future periods, my payoff is reduced. Right, so this is my immediate loss. Right, so the orange box there is my immediate gain from deviating. The red box is my immediate loss. Okay, and you might say, well, it's easy. When we look at that diagram, you say, oh, the orange box is smaller than the red box. The gain doesn't outweigh the loss, so we shouldn't deviate. But it's a little bit trickier than that. Okay, because we have to remember that these payoffs here were, you can think of them as dollars, or there were some nominal values, okay, nominal utility values. But we have to remember that people also have a preference for receiving things sooner rather than later. Okay, and it turns out this preference for receiving things sooner, that's going to turn out to magnify the size of that orange box. And it's going to turn out to shrink the size of that red box. Okay, so we're going to call this preference, right? And by this preference, I mean the preference to receive things sooner rather than later. We're going to refer to this as patience. You want to get things sooner, you're not as patient. You can wait and you can get things later, you're more patient. Okay, the technical name for this is time preference, okay, and it's related to the rate at which a person discounts future payoffs. All right, so I want you to think of a person's level of patience, right? How patient you are. I want you to think of that as being inversely related to the interest rate that you would be willing to charge somebody on a personal loan. Okay, and the idea would be that if you charge them a higher interest rate, okay, then you must want to be paid back faster, right? You're charging them a higher interest rate, which means they're going to have to pay back that loan faster, which means you must be less patient then in comparison if you were to charge them a lower interest rate. Right? So the higher the interest rate, right, the less patient the agent making the loan is because they want to be paid back faster. But on the other hand, the lower the interest rate, and the more patient the agent is. They're saying, hey, I'm going to give you a low interest rate. You can pay me back slowly. I don't need that money back right this second. Okay, so here's the trick. It may be the case that someone who is very impatient, right, might want to just take that orange wedge now, despite the fact that the red sort of seemed to outweigh it nominally in terms of the diagram that we had drawn. And it may be the case that the individual doesn't place much importance on weighing future payoffs. Right, and one situation we sort of discussed in the case of finite repetitions was that it may be the case that the individual doesn't really believe the world is going to be around tomorrow. Okay, and you can imagine that's a little extreme, but if somebody believed that, they wouldn't care about waiting a long time to cooperate. They wouldn't care about that red region where they're losing that future payoff. They would only care about what they get today. They would only care about that orange box, and hence would be willing to deviate because they don't believe that there is any more future. They don't put any weight on these future payoffs. Okay, so that's one possibility, is that someone's very impatient. It magnifies this orange box, shrinks the red box in a way where now the orange box becomes more attractive. All right, and unfortunately, in order to discuss this idea of psychological weighting of payoffs over time, we're going to have to sort of take a bit of a technical hiatus here and discuss the idea of discounting. Okay, so how do we value benefits if they flow to us at different points in time? Well, we're going to introduce the concept of present and future values from sort of a finance perspective, but then we'll bring this back into a game theory discussion. Okay, so idea here now is that because the infinitely repeated games require players to compare payoffs that are occurring now at dramatically different points in time, right? They're playing forever. Okay, so now they're comparing payoffs that occur at dramatically different points in time, which means that they are going to treat these payoffs subjectively a little bit differently, right? When I get $1 today versus $1 tomorrow, I don't weight those things equally psychologically. I would, everyone, all other things being equal, people prefer to receive things sooner rather than later. Because if if someone gives you $1 today, you can invest it. You can turn that dollar into more dollars by tomorrow. So, all other things being equal, people have a preference for receiving things sooner rather than later. Now, we didn't worry about discounting in the finitely repeated games. Why not? Well, because there was no future at some points. Discounting wasn't an issue. In the last period, there was no future, and that's what we had used to backwards induce the outcome of that solution. All right, so let's talk about future values for a little bit. If I took PV dollars, so PV is going to stand for the present value of my account. So if I had an account with PV dollars, and I let it sit in that account for 1 year, compounded annually, what was the future value of that account at the end of the year if the interest rate is R? So we ask this question, and it's pretty easy to answer. Okay, if I leave it in at 1 period, okay, then I'm going to get back what I had in there, plus I'm going to get back R times what I had in there originally. This should be red. Okay. So this is the future value of the account after 1 period. And we could ask, all right, well, what happens if we leave it in there for 2 periods? Okay, and you'll notice all I did is I factored this PV out in the 1 plus R term. But if we left that same amount of money in the account for 2 periods, and we wanted to know what is the future value of it, and then we could do this computation fairly easily as well. Right? And we multiply, so here's 1 period, I got 1 plus R times PV, and then I leave it in again, and you'll notice things simplified actually very nicely, and after I leave it in for 2 periods, I get a very convenient expression for the future value after 2 periods. It's this factor 1 plus R raised to the 2 power. Okay, which means then we can sort of make an observation that it should be pretty easy to generalize to T periods then, right? The future value after T periods should just be equal to that factor 1 plus R raised to the T power, multiplied by whatever the present value was. Okay, so given a present payment, we should be very easily able now to project that payment into the future and compute its future value by multiplying it by this factor 1 plus R to the T. All right, likewise, given this relationship, we could actually flip that question on its head and ask ourselves, for a given future payment, what is that worth today in terms of the present value? Right? So we can just solve for PV in terms of future value. Okay, and we can sort of see now that if you want to project a value forward into the future, okay, we're going to multiply by this factor 1 plus R. Okay, now this second equation that we had just derived here tells us that if I want to take a future payment and project it back into the past or back towards the present, okay, then I'm going to sort of do the same thing, except I'm going to divide by the factor 1 plus R. Okay, so multiplying by that factor brought us into the future. Dividing by that factor brought us back into the present. Okay, and in a second, I'm going to define a factor here called 1 over 1 plus R. I'm going to call this the discount factor. Just note that dividing by 1 plus R later on is going to be the same thing as multiplying by this factor delta. Okay, so just don't forget that. If we want to go forward 1 period, we multiply by 1 plus R. If we want to convert the cash flow back 1 period into a previous period's dollars, then we can divide by 1 plus R. Okay, now, when we're playing this infinitely repeated game, we're not just getting one payment in the future. We're actually going to generate an entire stream. We're getting a payment for our payoff from every round we play. Okay, so we're going to have to compute the present value of the entire stream of payments. This essentially is going to allow us to convert all the future payments into present units, into present utility, which we can then sum up to compare the cash flows from different strategies. All right, so if we're given a stream of cash flows occurring at different times, okay, then we're going to, again, convert them all into present values, add them up, and we call this summing of the present values, taking the net present value of the payoff stream. Okay, so I'm going to refer to this then as the NPV of a cash flow stream or of a benefit stream as the net present value. Okay, so for now, let's consider the following benefits flow. So x0, x1, x2 out to xt. These are, you can think, utility flows or cash flows that are generated in the future by a particular strategy you play or by a particular investment. And the way we're going to compute the value of this cash flow is simply by just summing up the present value of each one of these cash flows. So you'll notice the cash flows that are coming in the future are going to be discounted. They're going to have a higher power, a higher T in the denominator. And as I mentioned before, we could also define this discount factor delta as just the inverse of 1 plus r, so 1 over 1 plus r. And then I can actually rewrite the net present value in terms of this discount factor delta. And we can do that again because multiplying by delta is the same thing as dividing by 1 plus r. All right, so you might ask, why is he doing this? And it turns out to make things, again, a little bit mathematically easier. And I am going to use this delta notation from here on out. So just it's important now to remember how delta and r are related. If I know one, I know the other. So we're going to use delta now, and if you ever want to get r back, I can use this relationship to solve for r. Okay, so r is what we're referring to as the discount rate, is the subjective discount rate. Okay, and so you can think of it as the psychological interest rate that somebody uses when they're discounting a future stream of benefits or a future stream of payments. And I'm going to differentiate now between the discount rate R and the discount factor delta. Okay, so delta is the psychological weight that an individual is placing on a future cash flow, right? We're calling it the factor. Why? Well, because it's being multiplied by each cash flow payment, okay, or by each benefit payment that's coming in terms of calculating that net present value. Right, so that factor, again, we're multiplying it by each payment. It's deflating the future payments by converting them back into their present values. All right, now one thing to note is that if the interest rate is positive, if R is some positive number, okay, which it should be if we're dealing with a nominal interest rate here, okay, then delta should be some number between 0 and 1. Right, if R is positive, okay, right, the lowest it could be is maybe approaching 0, would put delta close to 1. Okay, but certainly as R gets bigger and bigger and bigger and bigger, it makes delta get smaller and smaller and smaller and smaller and smaller. Okay, so formally, it's got to be the case then. If delta is some number bigger than 0 and 1, it must be the case that when I square it or cube it and raise it to higher powers, the result must be getting smaller. Okay, meaning that an individual, when they're computing their present values of cash flows coming way in the future, okay, they're going to be using much smaller weights, okay, for future cash flows compared to the weights they would be using on cash flows that are coming sooner. Right, so because of the fact that R is positive, okay, that means delta is going to be between 0 and 1. That implies then that people are going to behave in a way where they're putting less weight, less importance on future payoffs, and more weight, more importance on things that are coming now. Okay, so I'm going to make an argument now that we can think of delta directly then as really a measure of patience, right? It's an index. It's some number that's between 0 and 1. And we know the closer it is to 1, when R tends to be low, the more weight future payoffs are going to receive in that net present value calculation, which means the more patient the individual is going to be in discounting the future, right? We said when the interest rate is low, people are patient. They don't need to be paid back right away. So a low R corresponds to a high delta. Okay, so the closer delta is to 1, the more weight people are putting on future payoffs and the more patient the individual is in discounting. Hey, on the other hand, if delta is very close to 0, that must mean R is very high, and hence the agent must be placing a lot less weight on future payoffs and then is behaving less patiently, right? If they had a high interest rate, then they want to get paid back quickly because they're not that patient. So again, if delta is very close to 0, people are putting less weight on future payoffs, and the individual is less patient. Okay, so I just consider the two following sort of extreme observations here. Let's consider the case first. We know R's got to be positive, but let's suppose it went to 0. Okay, then delta is going to approach 1. Okay, meaning, I'm going to argue that the agent must be infinitely patient, right? If delta is approaching 1, if delta is 1, then delta squared, delta cubed, delta to the 4th, delta to the t power, they're all going to be equal to 1 also. Meaning the subjective weights that are multiplying each of those future payments are going to be the same. The individual's giving identical weight to present payments and future payments. So you could think if an individual is weighting the present as the same as he's weighting the future, he must be very, very patient. Okay, on the other hand, we could consider an individual that's maybe infinitely impatient, that has such a high interest rate that's driving his delta all the way down to 0. And you should be able to check that if delta is all the way down at 0, then the weights that are going to correspond, that are being multiplied in the net present value calculation, these are all going to be equal to 0 as well, except for that first term, delta to the 0 power, which will be equal to 1, meaning you will only care about payments that are being received now. Okay, so we want to use the Folk Theorem, right? And we know that we picked a strategy from an infinite set of possible strategies. Okay, but just recall that we picked a strategy that satisfied a particular condition, right? The strategy gave us a payoff vector that fell in that purple region, that feasible, individually rational region. And all we need to check now to find the subgame perfect equilibrium is to verify that there's some threshold level of patience, and we're going to use the value delta here to denote the value of patience, okay, such that we could support the strategy of cooperating forever against the threat of this grim trigger punishment of being punished forever if anybody deviates from cooperation. Okay, so just to recall, we already did pick from this set, right? We picked that top right point. Okay, so we're going to choose a payoff vector in that region by pinning down a particular strategy. So the strategy, don't forget, that we're looking at now is trying to cooperate in each period where both players choose C. And now all we have to do, since we're satisfying condition 1 of the Folk Theorem, is ask ourselves, for what value of delta would players also satisfy condition 2? Okay, for what value of delta would players be sufficiently patient in order to sustain this? Okay, so here's where we're going to go next. We're going to ask ourselves, for what value of the player's patience, delta, would guarantee that cooperating is more attractive than deviating? Meaning, we're going to ask ourselves, for what value of this discount factor delta would make the cash flow or the benefit stream from the cooperation regime more attractive in terms of present value in comparison to the benefit stream that would be generated if you were to deviate and then be punished forever. Okay? So here's our task. We want to find values of delta such that cooperating in every round is optimal in comparison to the option of deviating and being punished. And again, big assumption here is the punishment phase being the grim trigger punishment phase. But as I mentioned before, that's going to allow us to establish a lower bound on this threshold value of patience delta star. Okay, so let's get back to it. All right, so all we're going to do now is we're going to compute the present value, net present value of cooperating forever at CC for just one of the players, right? It's going to be the same for both players because the game is symmetric. So from one player's perspective, the payoff must be the stream, right? You're going to get 5 forever. And you might say, man, forever is a long time, right? I have a delta to the infinity there, and just FYI, I am abusing notation here just a little bit. Okay, really, we would be taking the infinite limit of the sum, but I'm going to abuse notation here, and we're going to take delta to the infinity power. And one thing, again, that's important to remember about delta is that it is some number between 0 and 1. Okay, which means when I square it, cube it, raise it to higher powers, it gets smaller. So if you take the limit as delta goes to infinity, that thing is going to approach 0. Okay, and that's actually pretty important to know because hopefully you remembered that this infinite sum here turns out to be an infinite geometric series. Okay, and it turns out because delta is between 0 and 1, it actually converges to a finite value, and that value is 1 over 1 minus delta. And we can actually prove this very, very quickly here. If we allow A to be this infinite sum term, okay, 1 plus delta squared out to delta to the infinity, and we subtract from it itself multiplied by delta, right? So if I multiply this whole thing by negative delta, I'm going to get a negative delta here, a plus delta squared cubed, so on and so forth. So essentially that 1 is going to go away. And all I'm going to do is subtract the bottom line from the top. So you'll notice on the left-hand side when I do this, the left-hand side I'm going to get a minus delta a. And on the right-hand side, I actually just wind up with this 1, right? That 1 falls down. And all those other terms with the delta actually wind up canceling each other out. Okay, and just remember here, delta to the infinity here, what we multiply by delta, that's really delta to the infinity plus 1, okay, which I'm assuming is delta to the infinity. So a little bit of abusive notation here, but gets us to where we need to be, which means then we can substitute this back in to our expression and replace this messy infinite sum up top with a very nice, neat expression for the net present value of the benefit stream of cooperating forever. It's just 5 over 1 minus delta. Okay, now we're going to do the exact same thing. And we're going to compare this present value to the present value, net present value of the benefit stream if we were to deviate, get that payoff of 7, but then be punished forever where we're knocked down to a payoff of 1. Okay, so we're just going to compare this present value from cooperation to the present value that we get when we deviate. Okay, so just note there's a little bit of difference here. So right away when we deviate we get 7, but in the future then we get 1. So if you look at this line here, I can actually factor out a delta from every one of those, and then I can apply the convergence series result on the previous slide. Sorry. So we factor out this delta, then I'm going to factor out that 1, and I can get a 1 plus delta squared plus delta cubed, and once I see that, that's that A expression we had in the last slide. I can plug that in here, and I get a very nice, neat expression for the net present value of deviating. Okay, right down here. Okay, so here's what we're trying to do. We want to find the level of patience that would support cooperation as the optimal strategy, meaning we want to essentially find the delta that would make the present value from cooperating bigger than the present value from deviating, right? If cooperation is going to be optimal, it should be the case that no player has an incentive to unilaterally deviate, right? And that's our definition, really at the core of what a Nash equilibrium is, which means we want to find a range of deltas such that the present value of cooperation is greater than the present value from deviating. If that's the case, okay, then my best response is to cooperate. My utility maximizing action is to cooperate here as opposed to deviate as a rational individual. Okay, so we just want to find the range of delta that would support this option of cooperating being the best thing to do. Right, so if this inequality holds for all players, then that means for every single player, the better thing to do is going to be to cooperate, which means we've found a level of patience that would be able to sustain the cooperation. Okay, so here's what we have figured out. That the strategy of cooperating for both players in every period, this is only going to be a subgame perfect Nash equilibrium, provided this inequality holds. All right, so what we're going to do now is we're going to substitute in the values that we had computed from the previous slides for each of these benefit streams. Okay, so one thing to notice here right away is if delta was low, right, we know delta, if it's close to 0, that means we're very impatient. Okay, if delta is close to 0, you'll notice the left-hand side becomes 5. The right-hand side becomes 7. Okay, which means the better option would be to actually deviate. So if delta was close to 0, that means the player is very impatient, and if he's very impatient, deviating is going to be more attractive. Okay, you'll notice if you take the limit as delta goes towards 1, then the left-hand side actually becomes bigger. So if delta is closer to 1, the left-hand side's bigger. If delta is closer to 0, the right-hand side's bigger. Okay, which means there must be some sweet spot, right, where the present values are just equal. And we can figure out what this sweet spot is analytically by just being careful with our algebra. So the next thing I'm going to do is I'm going to multiply through by 1 minus delta. Okay, you'll notice since delta is between 0 and 1, 1 minus delta is also going to be a positive number. So this is a legal move for me. I can do that. Okay, and when I do that, I'm going to get that 1 minus delta term multiplied by the 7. I can distribute the 7 in. Okay, and then we can combine all the delta terms, move them to the left. And then last but not least, divide through by the constants to find that as long as delta is bigger than a third, cooperation will be the more attractive option. Okay, so what we just figured out is that if delta is bigger than a third for both players, okay, they will both prefer to cooperate rather than to deviate under this threat of permanent punishment. Okay, so just to recall here, this was our informal definition of the Folk Theorem. Okay, we'd done a lot of work with the first condition, which was making sure we were picking a strategy that gave us a payoff vector where everybody was happy. Okay, and now what we just figured out is exactly what we meant by all players being sufficiently patient, right? What do we mean by that? Well, we meant that they must have a delta close enough to 1. Okay, what was close enough in this example? Well, in this example, close enough turned out to be bigger than this threshold value of a third. All right, but 2 steps to the Folk Theorem, right? I got to pick a strategy that's going to make everybody happy in the sense that they're getting an average payoff that's at least their min-max payoff. Okay, and once I pick that strategy, then the Folk Theorem tells me I can compute some threshold value of delta above which players would be willing to sustain that strategy as a subgame perfect equilibrium. Okay, so let's interpret our solution a little bit more here. Okay, recall we picked a strategy that kept everybody happy. Everyone was getting at least their min-max payoff. Okay, and we just solved then for the minimum level of patience above which all players would be willing to cooperate at that strategy. Okay, and again, a part of our model here was that punishment phase. We assumed that grim trigger punishment, right? And as I mentioned before, if the punishment was not as harsh, then this threshold value would actually go up, right? Because if the punishment is not as harsh, I'm going to be more likely to cheat, which means I would need the players to be even more patient, to have an even higher level of delta to keep them from succumbing to that temptation of cheating. Okay, so we did find this range of patience that does satisfy condition 2 of the Folk Theorem. Okay, so our final conclusion here then is that it is indeed possible to support, in the infinitely repeated prisoner's dilemma, the strategy profile of playing cooperate in each round for both players as a subgame perfect Nash equilibrium, again under this assumed threat of grim trigger punishment, provided that both players have discount factors of at least 1/3. Okay, so I just want to talk a little bit more about the stability of cooperation and how, how the ability for us to have sustained cooperation in the infinitely repeated game was very closely tied to this psychological element of the players, and that is how patient they are. Okay, so here's what we had just figured out. We said if any player in this game, as long as they have deltas above 1/3, they would be willing to cooperate at CC as opposed to deviating if they face a threat of punishment of getting knocked down to that payoff of 1 forever. So this is what we had just figured out. As long as their deltas fall in that region to the right there, these players are going to be willing to cooperate. All right, so let's take a look at a couple situations where cooperation would actually break down in this game. Okay, so here's a situation where both players' deltas are actually lower than 1/3. Okay, notice if each of their deltas is lower than 1/3, that means the net present value from deviating from that stream actually is going to be greater than the net present value of the payoff stream they get from cooperating. Okay, so in this particular case, unfortunately, both players would actually rather deviate than cooperate. Okay, so we would get a breakdown of cooperation in this case. Okay, here's a situation where player 2 is willing to actually cooperate. Right, player 2's delta is in a region that makes the present value of cooperating greater than the present value of deviating. However, player 1 is not willing to cooperate. Player 1 is very impatient compared to player 2. Player 1's delta is very low. He's closer to 0. So he's putting less weight on those future payoffs. And unfortunately, what that means is when he does that, when he puts less weight on future payoffs using a lower delta, his present value calculation of the payoff stream from cooperation is not as big as the present value of the payoff stream from deviating, which means it would be in player 1's best interest to deviate here. Okay, we can consider another case where player 1 and 2's roles are switched, okay, but the same explanation applies. Here, player 2 is the impatient one. He's willing to deviate and try to steal the pie, but player 1 is actually willing to cooperate. He's patient enough in that his delta is high, and the present value of cooperating would be greater than the present value of deviating from player 1's perspective, but not player 2's. Okay, last case is what we had actually just solved for. Okay, what we just solved for was this situation here, okay, where we show that if both players have a delta that is above this threshold value of 1/3, okay, then we can support cooperation as a subgame perfect Nash equilibrium. We can support the strategy profile of playing C in every period as a subgame perfect equilibrium, again, under this assumed threat of grim trigger punishment. Okay, so I want to just say a couple things about patience and stability, and then we'll wrap up. We're approaching an hour here, and I want to get this done. So I want you to imagine that everybody, in the population has some different value of delta, right? Delta, it's a psychological parameter. It's how patient you are. You wake up in the morning. That, if you're in a good mood or bad mood, it could determine your delta. Okay, but I want you to think, let's suppose that everyone's delta was distributed according to some population distribution, maybe some normal distribution or some symmetric distribution or some distribution. Okay, but imagine we could draw that distribution, right? There's all these people with deltas. Some people are very patient over here. Okay, some people are very impatient. Most people are somewhere over here. Okay, but given this distribution, Hey, we can ask ourselves, for this particular game, hey, how many people would actually be willing to cooperate given this distribution of deltas? Okay, and what we can actually see here is it's got to be just a fraction of people that are under this population curve that have some threshold value directly to the right. Okay, now one thing you'll notice is that if the threshold value of delta star goes up, right, suppose for example that delta star had maybe increased, let's say to 2/3, and you should notice right away that the cooperative sustainable region has gotten smaller. There's going to be fewer people in the population then, given that distribution, that have a delta somewhere in that range where it's possible to cooperate. Furthermore, hey, the region where people have deltas where cooperation is unsustainable, that has actually gotten bigger. Okay, so just to sort of conclude here with a closing remark, what we had just sort of noticed is that there's a very close relationship between an individual's psychology in terms of how patient they are and the stability of them cooperating in a repeated game. Okay, so what we just saw here is that the higher the threshold value of delta star is, the less likely there are going to be people that have a delta that randomly winds up to fall in that interval. Right? That interval becomes smaller as delta star goes up. Okay, so we can definitely relate the idea of a player's subjective level of patience to the stability of cooperation in this infinite horizon framework. And this is a very big idea here that we're going to conclude with. So, idea is this: the more patient the players are, the more likely they're going to have high deltas, which means the more likely they're going to have deltas that actually fall in this region where they have a delta bigger than that threshold value. Okay, so the more patient the players, the more likely it is that we're able to sustain cooperation. Okay, on the other hand, the less patient the players are, the more likely they're going to have deltas that fall in this interval 0 to delta star, which means their deltas fall below that threshold value. Okay, making cooperation unsustainable. So now the idea is that the less patient the players are, the more likely that cooperation is going to be unsustainable. Okay, so the harder it is to have sustainable cooperation. And we're going to see all these ideas again when we come back and tackle infinitely repeated oligopoly models. So I hope you enjoyed the video segment. I know it's a little bit longer and a little bit more technical than when we had analyzed the finite case, but this is it. This is all I would like you to know for when we come back and apply this to oligopoly.